Okay. Hello, everyone. Welcome to my talk. So let's get started. Today, I'm going to present Case Scheduler, a generic and effective sys scheduler for fuzzing with graph centrality analysis. Fuzzing is a popular technique to find bugs through mutating a set of sets. Here is a simplified workflow for fuzzing. It starts with a set corpus consisting of multiple sets, as shown here. Then we have a set scheduling module. We'll choose optimal set. Then the fuzzer will generate a large number of mutations to see if there are any interesting sets has been found. In this process, a critical component is set scheduling because it can greatly affect fuzzing performance. Sys scheduling. So what is sys scheduling? It determines the order in which sets are selected. Specifically, it will compute a weight for each set. Then it prioritizes with higher weight. Then why is it important? Further explore new code through set mutations. In practice, we found mutations from a good set can lead to discovery of more code, while mutations from a bad set can result in discovery of less code. And the goal of fuzzing is to explore program code as much as possible. Hence, a good scheduling strategy can greatly boost fuzzing performance. There are many research works in sys scheduling. We summarize their scheduling strategies in this table. For example, FLFuzz prioritizes sets which hit rear passes, and FairFuzz prioritizes sets which hit rear edges, and other fuzzers like EcoFuzz, Entropy, and Tortillas Fuzz employ different scheduling strategies such as number of discovered paths or entropy of discovered edges or hit count of security-sensitive coverage. All of them focus on historical mutation data while ignoring the structure of the control flow graph. Control flow graph in set scheduling. So why CFG matters in set scheduling? The answer is the CFG can reveal potential code coverage gain from mutating each set. Let's look at the example on how CFG reviews potential code coverage gain. Say we have two sets in our set corpus. Shown this, on the right we have a control flow graph of a program. We mark visited nodes in white and unvisited nodes in gray. Note that in fuzzing, we only care about unvisited nodes because we want to explore new code. Here is the execution path for set 1, marked in blue. We can see its execution path is directly connected to a single unvisited node, as marked in red circle. For set 2, its execution path is shown in red. We can see it is close to 3 unvisited nodes. For this example, intuitively, we can know set 2 is a better set because the goal of fuzzing is to explore more unvisited nodes, and set 2 is close to more unvisited nodes. However, existing works might choose set 1 because their decisions are made based on pure mutation historical data without consideration of the structure of the CFG. So we know CFG is important to set scheduling. Then an ideal set scheduling should incorporate the information of CFG. Then the question here is, how to use the CFG in SIS scheduling. Well, a naive approach is simply traverse the CFG and count the number of reachable and unvisited nodes. But there can be many problems with this approach. First, the graph can be large on real-world programs, and each SID requires a graph traversal, which makes the process very expensive. Second, the unvisited nodes are dynamically changing during a fuzzing campaign. Hence, we cannot cache the intermediate results and to reduce the expensive runtime overhead. And third, the counting treats all unvisited nodes equally. But in practice, some nodes might be guarded by super complex or super hard or even infeasible path constraints, which make it almost impossible for fuzzer to flip or reach. Then, instead of this expensive graph traversal and counting, maybe we could try to approximate the count. An approximate approach. The approximate count, we would like it should determine SID weight. Moreover, we would like the approximate count to have some desired features that is suitable to SID scheduling. We show these desired features as follows. The approximate approach should increase SID weight if there are more reachable nodes from a SID. Meanwhile, it should decrease SID weight if there is a node is hard to reach by a fuzzer. In this way, we can avoid waste too many mutations on some complex and hard branches. We also want the approximation approach decrease SID weight if a node is far away from a SID. Because in fuzzing, a faraway node is less likely to be reached. In the end, we would like this approximation approach to be efficiently computed on large CFG, because in fuzzing, SID scheduling is frequently invoked. We observe graph centrality can actually provide this nice and desired feature to SID scheduling. Hence, it is a natural fit to our need. A little bit background about graph centrality. It is a common metric in social network analysis. It measures influence of each node. It is often used to identify important nodes. On the right, we show a graph example of the graph centrality analysis on a social network graph. Each node represents a person, and the edge indicates connections between the people. The node size is proportional to the centrality score, and the larger node size indicates higher centrality. For example, the center people marked in the red circle is outgoing people, is outgoing guys, maybe some like a social media influencer, a lot of friends, and he has the largest centrality score. While introverted people, like shy people who have fewer friends, might have lower score. In this work, we use cost centrality to approximate code coverage gain for each SID. For more information about the cost centrality, please check our paper. However, there's still one challenge. The conventional CFG is not suitable to graph centrality analysis because conventional CFG contains visited nodes, while we are only interested in unvisited nodes. Because in fuzzing, our goal is to explore unvisited nodes. Second, there is no SID information in conventional CFG, but we need to compute centrality score for each node, for each SID. Our solution is to build a novel edge horizon graph composed of only unvisited nodes and seed nodes. Here is an example of edge horizon graph. On the top, we have two seed nodes represent two seeds. And on the bottom, we have four unvisited nodes marked in gray. Then we perform graph centrality analysis, like this. We can have a weight for each node. From this weight, we can know that seed 2 is a better seed, since it has higher score and indicating that it can lead to larger code coverage gain. We show the overview of case scheduler. First, case scheduler takes in the CFG and the initial seed coppers to build an edge horizon graph. Then it performs graph centrality analysis to identify the optimal set. Further, we'll generate mutation to see if there any interesting seed has been found. If there is, then new seed will be added to seed coppers. We'll also add the newly discovered nodes to the visited node set. In the end, we'll update the edge horizon graph on the fly with the new data of seed coppers and visited node set. Next, I will briefly explain how to build an edge horizon graph. We first classify nodes in CFG as visited and unvisited, like this. First, obtain execution paths for seed 1, obtain execution paths for seed 2. Then we just mark all visited nodes in white and unvisited node in gray. Second step is to identify edge horizon nodes. Edge horizon nodes are unvisited nodes whose parent nodes are visited. They form the boundary between visited nodes and unvisited nodes. In this graph, we can find two edge horizon nodes, are shown in red. Next, we remove unvisited nodes. We remove visited nodes from the CFG, like this. And the first step is to insert seed node. We first insert two seed nodes representing the two seeds in the coppers. Then we connect seed node to their directly connected edge horizon node, like this. In the end, we can have an edge horizon graph. Lastly, we also remove cycles from edge horizon graph. Since our example here doesn't contain any cycles, for more detail, please check our paper. Let's look at our evaluation results. We integrate case scheduler on LibFuzzer, AFL, concurrent execution engine in the QSIM to demonstrate its generic usage in various fuzzers. The evaluation results also show superior performance of case scheduler over existing C schedulers. On LibFuzzer, we evaluate 12 programs from Google Fuzz Bench for 10 repeated runs and over 24 hours. Case scheduler increased feature coverage by 26% compared with entropy. We also evaluate in AFL Havoc mode. We evaluate case scheduler against 5 state-of-the-art C schedulers on the same 12 programs from Google Fuzz Bench. And the result shows that case scheduler increased edge coverage by 4% compared with the best C scheduler in AFL Fuzz. Interestingly, we also find case scheduler can even be used to prioritize paths for concurrent execution engine. Hence, we integrate on QSIM, and we run QSIM with case scheduler on 3 programs, and the results show case scheduler can improve QSIM by 36% edge coverage compared with default C scheduler over 24-hour run. in terms of runtime analysis, we break down the runtime of case scheduler into two parts. One is graph centrality analysis. The second part is fuzzer maintenance. Case scheduler adds at most 1% overhead for graph analysis and at most 2% for fuzzer maintenance. In conclusion, case scheduler is a generic sys scheduler for fuzzing, fuzzer, FL, and concurrent execution engine QC. Case scheduler approximates potential code coverage gain for each SID using graph centrality score. We open sourced case scheduler and reproduction package, including all the binary and SID coppers on GitHub. We're also working on integrating case scheduler to libfuzzer and libfl code repo. Thank you. I'm ready to questions.
Questions?
Hi, Sam from ETH Zurich. Great talk, very interesting. I was wondering, this event horizon graph is basically like one step away from the visited nodes, right? You only follow like one edge, and this is what you collect. I was wondering, as a trade-off, could you go further in this graph in order to trade a little bit of runtime, but you get more coverage?
Are you asking like how do we construct the edge horizon graph, since we only consider like?
No, I'm asking the edge horizon graph is like by following one edge, like at the boundary of what you have explored so far, and then you build this to build the graph. If you go like more steps, then you will get a larger edge horizon graph, and then maybe more accurate results on the node centrality. I was wondering whether this would actually help and whether you tried this out.
I see. So let me show an example my better. So here, this example of the edge horizon node. So basically, we only consider edge horizon node because we found edge horizon node dominate all the unvisited node set. That means if you want to reach any unvisited node, you have to go through this edge horizon node. And this edge horizon node has a really nice property is they form a boundary. Like they can, if you link this edge horizon node, they can split all the node as a visited node and unvisited node set.
Oh, okay. Yeah, I see. Makes sense. Thanks.
Yes, very good brief. I'm Wally Bernal, Office of Naval Research. So I was curious as to the any speed up on times in terms of code coverage. You showed a finite time period of 24 hours, but I was curious if using this you were able to, if you use a metric of determining the amount of code coverage compared to other baselines, and if you were able to have a speed up in terms of getting to the same amount of code coverage by some of these existing approaches.
Are you asking like achieve the same amount of code coverage, like how faster we can
faster,
do it?
yes.
Yeah, that's a really good question. Actually, there's some interesting finding I can show you here. So this is on the further 24 hours. You can find it's quite interesting. Is sometimes only 1 hour case scheduler can achieve almost 24 hours default or entropy schedule results. So you can check the first point. The first point indicates the 1 hour result of the feature coverage.
Yeah. All right, thank you.
Okay, so this is Joe from Purdue, and very good work. So I guess I have an open questions. So we know that sometimes the number of an age being covered may matter for the seed selections. So do you integrate this information in your algorithms, or how do you think about we count this in the future research? Because I know it would be a trade-off, because when we maintain the number of NH being covered will increase the overhead of the seed selections.
Yeah. So that part is actually this graph. So you can see the last column is called fuzzer maintenance. That is what you're asking. So basically, for the fuzzer maintenance part, we basically do is we need to track for each edge how many execution paths or how many test cases has been generated to test that edges. And that part actually is a runtime overhead. But we check on the leaf fuzzer and FL. So at most, this fuzzer maintenance, basically tracking the hit count for each edge, will at most 2%. So still in a manageable way.
Okay, so you mean you already considering this information in your or somehow selection algorithms?
Yeah. So we use a hit count. It's like for some branches, let's say we already hit like 1 million times, but the fuzzer still fail to flip that branch. That means it's too hard for current fuzzer mutation algorithm. If you continue doing to try to flip that branch, that is useless. So we try to deprioritize because that is too hard for the current fuzzer. So we do not waste too much mutation on that.
Okay, great. Thanks.
Looks like there's no question in the chat. Maybe as a chair, I also ask you a question. You talk about you use interprocedural CFG as the graph. So how do you handle, let's say, indirect call to build the CFG?
You mean how do we handle the indirect call? Yeah, that is hard. It's still open research problem. Currently, we ignore all the indirect function call, but we're planning to incorporate like more advanced static program analysis, pointer analysis to resolve this in the future version of the case scheduler.
Great. Let's thank Dongdong one more time. Next.